Hello, I'm Clayton Thomas. This is Structural Complexities of Matching Mechanisms, and this is joint work with Yanai Gonzarowski. So this is a paper about matching mechanisms. These are algorithms matching students to schools, workers to firms, and doctors to hospitals. And these are based on students' reported preferences over the schools. I'll give specifics on these exact algorithms as we go, but we ask students for their favorite, second, third favorite, and so on, and we have to come up with a way to assign students to their schools based on this information. These are consequential real-world decisions, so we have many traditionally economic concerns in this setting. So a question you can ask as a theoretical computer scientist is, in these large-scale real-world algorithms, are there complexity concerns? And computationally, maybe not. In kind of the largest instance we have, New York City, there's about 80,000 students per year. This is a large case, but it's tractable. We have a lot of compute these days. However, other concerns abound, and I argue through this talk and in this paper that many of them are fundamentally about complexity. So what are these non-computational concerns? Maybe predictability, which students get which schools, interpretability, how do we explain the mechanism's results, and transparency. Can we trust that the matching we got is actually the correct one? These have been salient both in the economics literature and in practice. We see things like popular blog posts telling people how to decode the tie-breaking lottery numbers used in New York City. We see thought pieces about the risks of non-transparent placement algorithms. And we see school districts making consequential decisions about which algorithm to actually use, seemingly for largely reasons regarding interpretability. This school district, Boston, writes the behind-the-scenes mechanized trading of one of the algorithms makes the student assignment process less transparent. And that was one of their reasons they chose the algorithm they did. So what's missing? Throughout this literature, what's still unexplored? Well, I believe it's a complexity viewpoint, that these are non-computational complexity concerns. And with a complexity viewpoint, we can set out formal objectives that we want to meet and get quantitative results on what meeting that objective actually means. We can think like cryptographers, complexity theorists, researchers in data structures or distributed computing, and we can define a framework or type of protocol performing a task and achieve a simple protocol successfully, or prove that any protocol that works has to be complex. So in the paper, we give a pretty broad investigation of this technique. We give these kind of four main comparisons that I'll give a little bit of a tour and a flavor for throughout the talk. But mostly through the talk, I'll highlight things as just three kind of higher level questions. First, how does one student's report affect the matching overall, giving a stylized insight towards predictability? Second, how do we explain students' matchings, reaching towards interpretability? And third, how do we verify that the matching we actually got is the correct matching, trying to address transparency. Through the talk, I'll just barely give some flavor of this predictability question. I'll cover in some depth this interpretability question. For transparency, I'll mostly just briefly mention it at the end. But I'll also remark here that this transparency notion can be modeled using traditional classical TCS. You have an off-the-shelf approach to getting this using non-deterministic communication problems. If I find a certificate showing that the matching is correct under classical verification interpretation of NP or communication version of NP, then in this setting, I actually may have something very useful. Parents truly may not care how you found the matching, what deterministic algorithm you used, but they may really care that you got it correct. So here's the outline of the talk, and with this, let's dive into the first question. How does one student's report affect the overall matching? So backing up a step, what even is a matching mechanism? So we're looking for a mu matching say N students to N schools. Let's denote the students by D and the schools as H, inspired by doctors and hospitals. One very basic mechanism to just show how these algorithms can work is called serial dictatorship, SD. This mechanism proceeds in some order, matching students to their top-ranked remaining school. So how does this look if we order the students as D1, D2, D3, and their preferences look like this? Then the matching we get, well, D1 first in line just gets their top choice. D2 can't get their top choice there, so D2 goes to their second choice. D3, similarly, their top choice is already taken, and they end up at H2. So this is a very simple example, very simple mechanism. So we want to know, how does one student's preference report affect the matching in SD? A naive approach to asking this question and formalizing it is to ask, how much can you affect the matching? When I change one student's preference, what's the maximal number of other students' matchings that can change? Now, it's not too hard, if you think about it, to write down an example showing that this effect size can be quite large. Here in this instance, what happens is each DI just goes directly to their favorite school, which is HI. But I've constructed these preferences in just such a way that if I change only the first person in line, Mr. D1, I change them to taking H2. Let's look what happens. D1 goes there. Now D2 is kicked out, no chance to get H2. D2 instead gets H3. And this propagates with D3 going to H4 and D4 going to H1. So what we saw here is that when I change just one student's preference, every student's match can change. This has been observed before, and it kind of shows that even this extremely simple mechanism looks very unpredictable and thus very complex according to this naive measure. Thus, instead of looking for the magnitude of one student's effect, we look at the structure of one student's effect. Now, what does this mean, the structure of one student's effect? It means we characterize this function, SD, when everyone else's preference, pref minus D, when this is held fixed. I characterize the function from D's preference report to everyone's matching. What we actually find is that there's a small O tilde n bit data structure that represents this function for any prefs of other people. I won't spell out exactly why this works, but the intuition is nice. It says for each D later on in the preference order, you only remember either their first remaining choice or one single backup choice if, depending on that first student's report, their original first choice is actually taken. So instead of having to record the entirety of pref minus D, this big omega n squared bit thing, our representation of this function uses only roughly O of n bits, just roughly linear in the number of students. And this is quite a big difference for matching mechanisms between n squared and n. This is an exponential separation per student, so there's quite some saving here. So we just saw this SD function kind of has a simple structure. What about more involved, kind of more real-world mechanisms and different types of effects? So this turns out to be a really rich story. This gives the first two results and comparisons in our paper. And there are some really nice bounds, really nice constructions, in my opinion, that shed some light on this thing. But the entire story is pretty involved, so let's defer to the paper to see how this effects story really fully plays out. Instead, let's move on to our second question. How can we explain students' matchings? And here we're going to look at more involved mechanisms than SD. We're going to show that you can explain the results of some of these mechanisms, but not of others. So a little more background. In richer settings than the SD settings, schools actually have preferences over the students as well. These are determined, though, by preset policies, things like the student's distance from the school and socioeconomic status. So we turn them as priorities. We call the school's preferences over the student's priorities. And additionally, a difference from the basic setting is that each school may have many students matched to them up to some fixed capacity, with the capacity also determined by preset policies. In this richer setting, there are two canonical matching mechanisms, DA or deferred acceptance, which optimizes for making the matching fair through a notion of stability, and top trading cycles, which optimizes for the students getting a student side optimal match, this TTC mechanism. So these are actually kind of the main characters of this complexity story, DA and TTC, the two more or less unique canonical mechanisms. So it's finally time to meet one of these main characters, and that is deferred acceptance. How does deferred acceptance work? You take the student's preferences, you have them propose in order of their preferences from highest to lowest, and schools hang on to the highest priority proposal they've seen so far up to their capacity. You just continue this process until every student is matched or has proposed to their entire list. This is a very canonical, widely taught algorithm. If you think you've seen it before, you probably have. For example, on this preference profile, here's how the matching process and the final matching works out. So we like DA because it produces a stable matching. There's no unmatched pair that would like to match with each other instead. Formally, no DH, where D would rather be with H than D's match. And H either has an open seat or prefers D to some student that they admitted there. That's an instability. In some settings, like doctors, hospitals, workers, firms, this is absolutely crucial for people to even follow the matching that you told them to use. Otherwise, they're just gonna match off market amongst themselves. In school matching, however, this has an important fairness interpretation. It says that no school that I want, that I prefer to what you told me to go to, admits any student of lower priority than myself. So that kind of gives meaning to the priorities in deferred acceptance. Additionally, we'll see next that it gives a way to explain the outcome matching. So given this stability property, equivalently define min H for each school H to be the student admitted to school H with lowest priority, or just set this to some empty set if H has excess capacity. It's not very hard to see that the matching is stable if and only if each D is matched to their favorite, their highest ranked school, where that D has higher priority than min H. So there's nothing deep happening here. It's just observing that if there was a case where D prefers this H and D is above min H, that would exactly constitute a violation of stability here. Okay, given this property that each D is matched to the favorite thing where they're above min H, Azevedo-Leshno proposed describing the DA matching using one priority cutoff per school by communicating min H for all schools H and allowing students to calculate their matching as mu D equals the max according to their own preference list of all of the schools where they're above their priority. And this is a very intuitive interpretation. I just kind of need to clear this min H priority threshold. But what is it actually doing? In what formal sense does this explain the match at all? As a starting point, certainly it's communicating the matching to students. However, let's think about this. Let's think about the complexity of communicating the matching to understand what's going on here. Suppose, the school district has already calculated the matching for themselves. They just want to tell now the students what is the matching that everyone gets. At a first glance, this problem doesn't look like you can say anything. This communication problem looks trivial. Because in the standard model, there are N students who initially know only their preferences. And it's not very hard to show, it's pretty intuitive, that roughly linear bits are both necessary and sufficient to tell each student where they're going to go. You have to say something for all of us. And this just equals the trivial solution of writing down the entire matching and having everybody just look it up. So how can we make this communication problem non-trivial? Since without assumptions, O tilde number of students are both necessary and sufficient. Well, we make two natural assumptions on top of the model. We assume that there are many more students than schools. This is plausible in real life where there are many schools, there are many students per schools. And for analysis, let's just say for the talk that there are n schools and n to the 10 students, way, way more. Second, we assume students start off knowing their priority scores at all of the different schools. For example, they could look these scores up since they're determined by policies. Alternatively, they could receive an email at the beginning of the school matching process where it just tells them, here are your priorities everywhere. Technically, we've already used into the 11 bits of communication to do this, but it's, I believe, fairly natural to assume that students can receive this information each privately or through the preset policies. So given these assumptions, it actually kind of becomes clear what is this Azevedo-Leshno protocol doing. It's accomplishing a somewhat significant feat under these assumptions. It's communicating the matching of all into the 10 students using only linear number of bits, O tilde n. This is a somewhat remarkable property, which next we'll investigate for other canonical mechanisms. So time to meet the second main character of the paper, finally. This is the top trading cycles mechanism. This is just a different mechanism for matching students to schools. You can calculate its outcome as follows. Have each student/school point to their favorite or highest priority remaining school/student. So each side of the market points against each other. There must be some cycles in this finite DAG without degree 1 everywhere. So pick any such cycle and permanently match each student in the cycle to the place they're pointing, the thing that the student wants. Just remove all of the matched students from the market, decrease the school's capacities by 1, and recurse, and continue this process until every student has matched or is going to go unmatched. On this same example from earlier, you can see TTC worked out here. And this just produces different matchings than deferred acceptance, in particular non-stable matchings. So why do we like it? We like TTC because it produces student-side Pareto optimal matchings. There's no mu prime different from mu that's weakly preferred by every student to the outcome of TTC. It's the more or less unique mechanism with this property that you would like to use, and this means it's both been very canonical in theory and useful in practice, although less favored than deferred acceptance. But note that it treats priorities completely differently from how DA does. A higher priority in TTC means I'll let you trade away your seat here earlier. And in particular, what worked for DA for communicating or representing things is going to have no hope for TTC. We have to start from scratch. And indeed, that's what Leshno and Lowe did in their paper. They found that the matching in TTC can be described using a priority cutoff for each pair of schools. You communicate these thresholds, let's call them by HK for each pair of schools HK. And now all students can calculate their match via the following. You still get the favorite highest ranked from some set, but now it's the set of H such that at some other school K, I clear the cutoff at K needed to kind of buy my way into school H. So if I'm over here at school A, that actually puts school B into this set for me. So again, what does this representation do? Unlike for deferred acceptance, I won't spell out exactly why this holds for DA, but the intuition is just the same thing interpreting the meaning of the priorities for TTC. It's that I can buy my way into the school. So what does this representation do? So recalling our assumption 1 and assumption 2, This result shows that TTC can be communicated to all n to the 10 students using only n squared bits. Now this is, much lower than n to the 10, but it's also much higher than for deferred acceptance. This is a few bits for each pair of schools. So I've really set up these pair of results to beg the question, can we explain TTC like DA? Can we get something lower than this n squared bit protocol that worked for TTC? And the main theorem that I want to sketch in this talk and in this part of the talk is that no, any way to communicate or represent TTC requires O of number of schools squared bits. Of course, formalizing this requires a formal model, but I'll just, for the talk, leave it up here and say that the main idea is that you post a Blackboard certificate C such that each student D can figure out their match from only C and what they're very plausibly assumed to know. They're assumed to know their own preferences. That's kind of always the case in these models, and we're also assuming they know their priorities at the different schools. And I don't want to give the exact proof of this theorem either. However, I would like to sketch how do we handle these weird, slightly novel type of protocols where there's many more agents than we have even bits in our certificate. Well, our one weird trick is just that we construct settings with n squared students whose matching is determined completely by other students. N squared distinct other students completely identify my own matching. And how does this look in our hard instance? Well, for example, this student here kind of makes a choice here, a binary 0, 1 between these two things. And this actually just completely determines the matching of this guy and this guy. So these people down here, their matching is completely determined by the top stuff. And we can see through this sort of sketch of the construction why with only n schools I can get this n squared bound here. And indeed, it means when we find a construction that looks like this, all of the n squared matchings must be communicated solely through the certificate C, showing you need 2 to the n squared distinct certificates. So this gives another one of the main comparisons in our paper, this contrast between TTC and DA. Okay, now let's move on to the third question. I'll just give a brief flavor of this right now, but the question is, how can we verify that the matching we found is actually correct? Well, we can extend the model we just looked at to ask what happens in kind of the more traditional TCS model with completeness and also soundness. So completeness is what we already had, which is that you can communicate the matching, say, in DA. Soundness additionally would say that if you ever select a certificate that is not inducing the correct DA matching, then there exists some student D who can check your certificate and just from their private information determine, no, this must have been wrong. There's no way this was the right matching, the right certificate. This is a lot like classical non-deterministic communication, but now we have prior known priorities and many more students than schools. And it's fairly easy to see if you know some stable matching theory that our representation that worked is not going to suffice for this problem. The reason is that there can be many stable matchings and the protocol would have done just as well representing all of them. For both TTC and DA, we get verification complexity theta of number of students, which is somewhat surprising and contrasts with Yanai's prior work showing an n squared lower bound when the priorities are unknown for the schools, when the priorities have to be communicated. This is the final main result in the main body of our paper, this similarity between DA and TTC. In the paper, in an appendix, we also explore the connection to a student's menu, the set of schools that the student could possibly receive, holding fixed the reports of all of the other students. This is something we looked at in detail in our previous paper. And these sets that are used in the communication representation protocols for DA and TTC, they kind of plausibly look like they should be these menus. You get your favorite thing from them. However, we observe that actually they're not. The menu in DA and TTC can be pretty unrelated from the sets constructed in those protocols. And in fact, we prove that representing all students' menus requires n squared bits even for DA. This one where we got this beautiful O of n representation of these other sets. So this gives a nice similarity also that we present in the appendix. So kind of recapping and towards the conclusion, real-world practitioners have observed that TTC is less transparent than DA. And picking up on this, theorists have said, well, we have here an O of n bit protocol for DA and an O of n squared bit protocol for TTC. Thus, the concern that TTC is less transparent than DA remains valid, as you can describe DA with one cutoff, but TTC requires a pair of cutoffs, a cutoff per pair of schools. Our work is the first to actually formalize this and give a lower bound that matches the complexity of TTC, this omega n squared. So this does formalize this distinction. It finally corroborates the concern with a rigorous model. But what I really like about it is in this extra context, it clarifies what does transparency mean in this context? What is the fundamental concern and how can we turn it into math? It's not that the school district can't cheat or the parents will know that this must be my match. And it's also not that these cutoffs show exactly what the student could have gotten by changing their report. In fact, the distinction between DA and TTC would disappear under these more stringent versions. It's just that you can check that your assignment was correct via a publicly posted and low bit complexity piece of information, these cutoff type scores. And so finally wrapping up, in our paper, we address predictability, interpretability, and transparency, all with novel, very TCS flavored models. And I had an absolute blast kind of exploring and fully fleshing out this space of things. And thanks so much for watching. Hoping to see everyone at STOC in person. Yeah.